Today is our first day of undoing the things we've been doing over the last 4 days. So over the last 4 days, we've talked about like terms, we've talked about simple exponent rules, we've talked about multiplying polynomials, and today we are going to undo um, multiplying, I guess. We're going to unexpand today. And what that's really called is factoring. So before we start off with the mathy idea of factoring, I want to look at generally what does it mean? What does a factor mean? Well, if you thought about it in the English language a little bit, if something is a factor, then it's a part of. And if something is a factor, it's definitely necessary. And if something is a factor, it's important. So an everyday example of this idea of, what does it mean to be a factor? I'm going to make this statement. Travis Lulay was a factor in the BC Lions winning last year's Grey Cup. And I think we'd all agree that was true. So in this idea of a factor, Travis Lulay was definitely an important piece of the entire team winning. He wasn't the only thing, but he definitely was an important piece. So mathematically, that's this idea of a factor as well. The mathematical definition of a factor is this: a piece of the whole that divides the whole. So not just any piece, a special piece, an important piece. So for example, 5 is a factor of 15 because 15 is divisible by 5. So there's our mathy definition that we're going to go with. And what we want to really be good at by the end of this unit is we want to be able to break the whole into its pieces, and that's what factoring is. So factoring is a very important mathematical process. It's something we all have to be able to do, and we all have to be able to do well, and you're going to find you're going to be factoring for the rest of your mathematical life. So it's the process of breaking a whole into 2 or more pieces. Two or more parts. For example, and then each part is a factor. Each part is important. And we've already been doing examples of wholes and parts, and we've looked at the area model of multiplication. So if I wanted to know the area of a particular rectangle, I think it would be really important for you to know the dimensions of the rectangle. So that kind of fits with our language definition of what a factor is as well. Now you guys have been doing factoring for a while now, I think since grade 6, and the way you've been looking at it is find the prime factors of numbers. You broke numbers into their smallest pieces. So here's 2 examples, and I'll do them differently, and you can find prime factors however you want. The first one we'll do is a factor tree. So with our factor tree, we break apart the things above into two pieces, and those two pieces multiply back to the whole. Again, they are factors of. But when we do prime factors, we don't stop a particular branch until we have a prime number. So 7 is a prime number and 2 is a prime number. And what you know from before then is you can then write 56 as a product. Remember, product is a multiplication word. So we want to make a note of that because we are unmultiplying from now on. So product is a multiplication word. Another way of writing 2 times 2 times 2 times 7 is 2 cubed times 7. Okay, well, there's another way to break up a number into its prime factors, and you can do this horizontally or vertically as I'm going to do it. And that's this idea of, well, just going through the process of breaking it up into its smallest pieces. Now each piece this way has to be a prime factor, unlike 7 times 8. 7 times 8 is not a prime factor. So we have to know a few divisibility rules, like numbers even, so it's divisible by 2, and so on. So we're going to keep on breaking this down. So every time I write one of the factors, I'm unmultiplying. I am dividing it out. And we get 12, and we get 6, and we get 3. And finally, when we can do no more, we stop. And as with a factor tree, we'd get exact same factors. We can write 96 is equal to 2 times 2 times 2 times 2 times 2 times 3, or 2 to the power 5 times 3. So remember, we talked about this before, but exponential form, the base tells you what you're multiplying, and the exponent says how many times. There's in this particular example, there's 1, 2, 3, 4, 5 multiples of 2. Okay, so this is what we knew starting grade 6. And given that you can break apart something into its smallest possible pieces, well, what we can then do is we can ask the question, well, what do these two things have in common? So this is our first and most important factoring technique that we're going to do today. We want to break things into pieces, and when we want to determine initially what's the biggest piece that goes into all of them. In this example right here, we've already done all the hard work. We know that 56 is equal to 2 times 2 times 2 times 7, and 96 is equal to 2 times 2 times 2 times 2 times 2 times 3. And if we wanted to know what the greatest common factor is, well, let's have a look at what that means. Greatest just means biggest. Common means the same. And factor means piece. So in finding the greatest common factor of 56 and 96 in this example, what we want to find is what's the biggest piece that goes into both of them, and it has to be the same. So what I like to do is help my brain and identify it somehow. So in looking at both of these, I know 56 has a factor of 2, and so does 96. 56 has another one, so does 96. 56 has a third one, so does 96. 56 has a 7, but 96 doesn't. 7 does not go into 96, therefore it's not a common factor, it's not the same piece. And similarly on the bottom, we have another 2, another 2, and another 3, or a 3, and we've used up all our factors above, so 56 does not have a fourth factor of 2, or a fifth factor of 2, or a factor of 3. So by highlighting, helping my brain, what this tells me is the greatest common factor of 56 and 96 is 2 times 2 times 3, which is 8. And again, what this says is 8 is the biggest number that goes into 56 and 76. Now that's great, but you've done that before. So let's take this to a grade 10 level. Well, in grade 10, we're dealing with polynomials, not just plain numbers. But we can ask the exact same thing. Find the greatest common factor of the following monomials. And in order to answer that question, what we have to do is break each monomial down into its prime factors. We got to break it down into those important pieces. And remember, those pieces are a product, which means when you put them back together, it's a multiplication. And then what we want to do is identify what they have exactly in common. So we can break apart 6x cubed y. Well, we can break apart the number into 2 times 3. And x cubed is just x times itself 3 times and times y. So here's the expanded form of that monomial. Similarly over here, the expanded form of this monomial is 2 times 5 times x times x times y times y. So we factored each into the smallest possible pieces, and now we're going to go and identify what things these two monomials have in common. Well, they both share a factor of 2. They both have 2 x's. And remember, when I say 2 x's, I mean it's really x squared, right? And they have a y in common. So just as with 56 and 96, what we can then do is we can say the greatest common factor, the biggest thing that these have in common is they have a 2, they have an x times x, and they have a y. So the greatest common factor between these two monomials is 2x squared y. Similar to numbers. Okay. This is what we really want to do though. We don't want to just deal with monomials, we're dealing with polynomials. So our first factoring technique that we're going to use for polynomials, remember polynomial is an expression that has one or more terms, and we're interested in more. Well, this technique of breaking things apart into its smallest possible pieces is going to be our first and most important technique. So we can factor polynomials pictorially and algebraically. So that should make absolute sense because remember, factoring is unexpanding, factoring is unmultiplying, and we learned or we reviewed multiplication using an area model and algebraically. And both of these approaches, regardless of the one you use or like or understand, they break the whole into pieces. So I just want to look at a couple of examples that illustrate how you can break a polynomial into pieces. And of course, I said before, rectangles are my favorite shape. So here's this general idea of how a rectangle can help you break a hole into pieces. As we know, the area of a rectangle is equal to L times W, one of the dimensions times the other one. And if I just wrote that out right here, that's what this would look like. And in the area model of factoring using the GCF, I'm going to be consistent. Each one of L and W is a factor. It's an important piece. And I'm going to set it up the same way all the time. L is always going to be the greatest common factor. And W is always going to be my other factor. And pictorially, they're the dimensions of a rectangle. Now, when we use the greatest common factor, the other factor cannot be broken apart any more than you write it down. And you'll see what I mean. Algebraically then, when we factor, we're generally going to get 2 pieces for us. And I'm going to try to be consistent. And the first piece, this is where we're going to have our greatest common factor. And this one here is going to be the other factor. So remember, factoring is unmultiplying. We are unexpanding. We are making brackets, not getting rid of brackets. And again, either way you do it, what I'm going to say is you cannot, this other factor cannot be reduced, cannot be factored anymore. And what we might think of this, we might think of it as being prime. Now, factors aren't prime, numbers are prime, but it's a nice way of thinking about it. So here's the two general methods. I'm going to go through two examples of each. Okay, so here is a binomial. And we've looked at binomials a lot in multiplication, and you might want to pause a sec right now and look at your notes, look at your homework, and get an idea of, well, what kind of questions gave you that answer? Okay, so if I look at an area model, 3x squared plus 6x, well, that's my stuff. That's what I have. That's my inside. And in using an area model, what I want to do is I want to determine the dimensions of my rectangle. Now I want to be consistent. I want to find the vertical part first, and I called it L. Now I don't want you to write this down for a sec, I just want you to kind of follow. If I were trying to figure out the dimension of the vertical piece of this rectangle, well, what I'd have to have is I'd have to have something that divides into both those pieces. So for instance, on the vertical right here, I could have a dimension of 3. 3 goes into x squared, and 3 goes into 6x. So 3 goes into x squared this many times. So I'm asking myself, what times 3 is equal to 3x squared? So you can think of that as multiplication or an unmultiplication, which is a division. As well, I can go, well, again, the vertical part right here is exactly the same as this one right here and as this one right here. So when I look at my next rectangular piece to the right, I ask the dimension has to be the same. So I go, well, okay, how many times does 3 go into 6? Well, 3 goes into the 6 2 times, and I have to have an x left. I have to have an x as well. And there's my dimension right there. So I'm either doing a little multiplication in my head, or you're doing a division. Now, one of the things I want to illustrate right here is, even though I've broken this rectangle into 2 dimensions, if we look at the top, they have something in common. That top has x. So when we factor using the GCF, what we really want to do is find the biggest thing that goes into both of those pieces. And a good way to make sure you've done it right is the other dimension is prime. So let me just erase this, and let's see if we can go at this properly. So we want to be consistent. We want to always find the GCF, and we want to find the biggest thing that goes into both those pieces. Well, 3 is the biggest number that goes into both those pieces. So 3 is a part of my greatest common factor, and x also goes into those pieces. So in this particular question, it's going to turn out to be 3x is the biggest thing that goes into both of those pieces. In order to figure out the top dimensions, well, you really have to do 2 mini little problems. So really what this is saying is, you can think about it this way. 3x times something is equal to 3x squared. And if you can do that in your head, of course, it's going to be x. 3x times x is x squared. The other way we could do it, instead of multiplying, thinking multiplication, is, well, we can unmultiply. And I guess in that sense, what we're asking is, what is 3x divided by 3x? The 3's cancel out, and one of our x's on top cancels out one of our x's on the bottom, and we are just left with 1x on top. Similarly, in the second little piece we have to figure out, what we have is, well, what is 3x times question mark is equal to 6x, while 3 times 2 is equal to 6, and x times 1 is equal to x. So we end up with a 2, or we're asking ourselves, how many times does 3x go in? How many times does 3x go into 6? 3 goes into 6 twice. Okay, so there's the pictorial, and I just want to remind you that, again, we want to take out the biggest piece that goes into both the pieces inside, and as a check, we want to make sure that the other dimension is prime. So what we can say then is 3x squared plus 6x can be written as a product of this piece times this piece. And what we've just done there is we have undistributed. We have undone the distributive property. So the nice thing with factoring is you can always check your answer by undoing what you just did. So there's a pictorial approach, and it's a little bit of a puzzle approach, but again, it's concrete, it's visual, and I hope understandable. Okay, let's look at the algebraic. Well, the algebraic method of factoring using this one technique is you break each piece into its prime factors, just like we did in the question on the previous page. And then what you do is you identify the greatest common factor of each piece. And again, I'll highlight it. The first term has a 3, the second term has a 3. The first term has an x, the second term has an x. The first term has another x, second term doesn't. The second term has a 2, and the first term doesn't. So what we've done is we've identified the greatest common factor. And what we're then going to do is we're going to take this out. Now, when I say take out the greatest common factor, that is really a division word. So when I take out the greatest common factor, I found one of the pieces, and the leftover, in this case what is not highlighted, we have an x, we have a plus sign, and we have a 2. That is our other piece, that is our other factor. So if I make a quick little recipe for that, because at the heart of it, factoring is a technique, it is a recipe. Here's what we did. We factored the terms. We identified the GCF. We took out, and again, I'll put that in bunny ears because we didn't take it out. Take it out seems like a subtraction. It is actually a division. We took out the GCF from each term, and that's what common means. And then we put the leftover stuff in brackets. And what that gave us is it gave us our other factor. So here's what I would like you to do when you finish watching the video. I simply want you to tweet. So here's what I want you to do. I want you to tweet to hashtag NickMath45 in the algebraic approach that I just completed that looks pretty straightforward. Factor each piece, identify the common factor, take out the common factor, and everything else left over goes in brackets. I want you to tweet me this. Everyone needs to do this. Why do we need brackets? So why do we need brackets? Now the first piece, notice I didn't put brackets around the first piece, but I could if I chose. So let's look at one more example. Two more examples. Factor this one. Okay, pictorially then, I break my rectangle into its two pieces. I always try to look at the GCF first, and I go, what is the biggest thing that goes into both of those? And I'm consistent. I'll do numbers and then letters, and I'll do letters in alphabetical order. So 6 is the biggest number that goes into 12 and 18. A is the biggest thing that goes into A and A squared, and B is the biggest thing that goes into B and B. So I've identified the GCF, and now I just try to find the dimension of both these little pieces separately. So that's one nice thing about doing the area model. You break a nasty problem into two simpler ones. So again, as I said above, this is analogous to finding the other dimension to go, okay, well, what's this? And when we do that, well, that's equal to 2. 6 goes into 12 twice, A's and B's cancel out. Then I go on to the next piece and I ask myself, well, what is 18A squared B divided by 6AB? 6 goes into 18 3 times, plus 3 times. A goes into A squared A times. So one of the A's cancel out and the B's cancel out. And what I end up with then is that 12AB plus 18A squared B is equal to 6AB, there's my first factor, times my second factor, my second important piece. And remember, the important pieces are the dimensions of a rectangle. Okay, let's look at the same question algebraically. Algebraically, we break the whole into all its individual little pieces. So 12 is 2 times 2 times 3 times A times B, plus 18 is 2 times 3 times 3 times A times A times B. We identify what they have in common. Has a 2 and a 2, has a 3 and a 3, has an A, has an A, has a B, has a B. The first term has a 2, the second term doesn't have another 2, and the second term has a 3 and an A, and the first term doesn't have another 3 and another A. So we found our greatest common factor, and our greatest common factor is the first factor of our binomial. That is 2 times 3 times A times B. And as it said above, then the leftover stuff is my other piece. I have a 2, a plus sign, and a 3 times A. And as we got pictorially, we get the exact same answer. So again, the nice thing here is both of these methods give you the same answer. I like the rectangles. The rectangle is really concrete, visual. It's not magic. I'm just finding 2 dimensions of a rectangle. Okay, let's look at one more example. This is a trinomial. It has 3 pieces. It doesn't matter. What I can do is I can simply break my rectangle into 3 little pieces. And here's my last piece. And I go about the same process. I find the vertical dimension. I go, okay, numbers with numbers first. What's the biggest number that goes into 25, 15, and 5? Well, that's 5. Looks at the m's. What's the biggest m that goes into m cubed, m squared, and m? Well, that's just m. And what's the biggest power of n that goes into n, n squared, and n cubed? Well, that's just n. And now what I do is I look at these 3 separate little things and I determine the dimension, the top dimension of each 3. And again, as you can think multiplication or division, but the top dimension of this is going to be what is 25m cubed n divided by 5mn. Well, 25 divided by 5 is 5. I have m cubed over m, so I have m times m times m on top and 1m on the bottom. So 1m cancels out, I'm left with 2 left over, and my n's cancel out. So there's my first little thing. And then I go ahead and do the exact same thing. I have negative 13m squared n squared divided by 5mn. Negative 15 divided by 5 is negative 3. m squared divided by m. One of the m's cancels out. N squared divided by n. One of the n's cancel out. I'm left with that. And then finally, notice how I'm keeping the symbols. Finally, I do this. And in our last one, 5 divided by 5 is plus 1. I'll write that. The m's cancel out, and one of the n's cancel out. So what I can say is, when I break this nasty looking expression into two pieces, one of the pieces is 5mn, and the other piece is my other dimension of my rectangle. And there it is right there. So that's the factored form. That's factoring completely that thing. Algebraically, this can be kind of messy, but let's have a quick look. Break apart each piece. Well, 25, 5 times 5, m, n, minus 15, 3 times 5, m, n, plus, well, can't break 5 down anymore, and we get this. So here's the prime factorization of that polynomial. Then we identify the GCF. They have a 5, they have a 5, they have a 5. They have an m, they have an m, they have an m, they have an n, they have an n, they have an n. The first term has another 5 and 2 m's, but the last term doesn't have any m's. So as soon as you identify one term that doesn't have what you need, then you can stop with respect to the GCF. So we've identified the greatest common factor. Then we can figure out the other factor, and the other factor turns out to be the pieces left over. So here we have 5mm minus 3m times n plus, because there's that plus sign, n squared. Now, there's a fast way of finding the greatest common factor. So there's a fast way of finding greatest common factor with respect to the letters. We don't have to expand everything out. That takes a lot of time, and we don't have to do it. So what I would hope you would notice is, with respect to letters, the greatest common factor is the biggest power that goes into all of the terms. So if you look at the first expression, m and n are in all of them. So if we look at the letters, m and n is in all of them. But in the first one, n to the power 1 is the power of n, and that's the one that turns out to be in my GCF. If you look at the last expression term, m to the power 1 is in that one, and that turns out to be the greatest power in my GCF of m. So there's a fast way of finding the letters. Look at the smallest exponent that of the letters they all have in common, and that turns out to be your GCF. Okay. In class, we're going to do a whole bunch of examples, because that's what we're going to need to do. But I'm hoping that you're seeing that the rectangles are intuitively a bit nicer. Okay, so here's our connections then. What we just did today and what we did before. Greatest common factor undoes the distributive property. If you look at all of the rectangles that I just drew, they're the exact same as when we did the distributive property. That's why I wanted to spend some time multiplying using rectangles. The distributive property is a multiplication word. Is a multiplication or expansion, expand word. and the greatest common factor unexpands. And what that really is it allows us to find the factors. It allows us to factor. So again, just to give us a pictorial approach, here's the distributive property. We know two parts, we know the dimensions, and we find the area. Well, here's what we did today. You know the area, and what I asked you guys to do is find W and find L. And we looked at it two different ways.